Alright, this is a lecture for BIO367 Microbial Diversity at Keene State College. This is going to be a 4-part lecture that addresses the fundamentals of microbial metabolism from a very theoretical and chemical perspective. By listening to all 4 of these lectures and by doing the associated Mastering Microbiology homework, these are the learning goals that I hope that you will achieve. You should be able to understand how to categorize microbes based on their metabolic diversity with emphasis on how they obtain energy and carbon. You should be able to calculate delta G values using theoretical free energy formation values for reactants and products. And we'll be practicing that a little bit together. I'll show you an example here and I'll give you some practice in class. You should be able to explain the idea of energy coupling, in other words, why cells need ATP. And you should be able to apply delta G values to answering the question, could a microbe theoretically reproduce in this environment? Which helps us to understand microbial evolution and their physiology and reproductive rates. It also helps us to understand the fates of different chemicals in the environment. We're going to review redox reactions and the term redox potential, and we're going to practice calculating delta G from delta E values. We're going to learn what an electron tower is. It's a concept that's really important in microbial metabolism, and we're going to learn why, and we're going to apply that concept to an understanding you should already have regarding intracellular electron carriers, in other words, coenzymes, for example, NADH. Let's get started. Okay, again, this is a 4-part lecture, and this is the first part. I'll be titling it 1A, the others will be 1B, 1C, and 1D, respectively. So one of the things that's really amazing about microbes, and that is a super important concept for students to grasp when they first start studying microbiology, is their completely and totally amazing metabolic diversity. It's why I call this class microbial diversity and not just microbiology, because if there's one thing you leave class with, that's what I want you to have some fundamental understanding of, just how metabolically flexible you see creatures in, the microbial world. So in order to get a handle on that, we have to have some terminology and some bins or some categories. And the binning or the categorization that we use are to consider how microbes get energy, how they get carbon, and sometimes separately how they deal with electrons. And that's what this figure is depicting. So you should know by now that all organisms need ATP and that ATP feeds into cellular work. And we'll talk more about that in this lecture as well. All organisms therefore need a source of energy. And the sources of energy that exist in the world are categorized as organic molecules, inorganic molecules, or light. If you're an organism that uses organic molecules as your energy source, you are a chemoorganotroph. So we are certainly chemoorganotrophs, for example. So are the yeast that we use to make beer. Chemolithotrophs are organisms that use inorganic molecules as a source of energy, so kind of as their food source, so to speak. And then phototrophs, of course, use light energy. So plants, of course, are phototrophs, but so are the cyanobacteria. Carbon sources, you know the importance of carbon. It's the building block from an atomic perspective of all life. So we can call organisms autotrophs or heterotrophs. You're an autotroph if you use carbon dioxide as your carbon source, and you're a heterotroph if you use organic molecules. So anything that does photosynthesis, as you have studied it, oxygenic photosynthesis, will use CO2 as their carbon source. So those organisms would be phototrophs and autotrophs. You could combine those two terms and call them photoautotrophs. In contrast, we get our carbon from organic molecules, things like glucose, and so do many, many microbes on the planet. From an electron perspective, the term organotroph means that an organism gets its electrons from organic molecules, and the term lithotroph indicates that the electrons come from inorganic molecules. In a lot of textbooks, they won't separate out the electron source. They'll simply, it's simply known that the electrons come from the molecules that are usually providing energy, but that's a little bit different in the phototrophs, which will still need a source of electrons ultimately. So those are the categorizations from a metabolic perspective for organisms, and certainly for microbes. We're focusing on microbial metabolism, really just fundamental metabolism. And at the heart of all metabolism are chemical reactions. Chemical reactions are important for living things because they can be harnessed to allow cells to make ATP, and then they are used in turn to use ATP to do cellular work. So if you think about metabolism, it can be broken down into two arms. It can be broken down into anabolism, and it can be broken down into catabolism. So catabolism means that you're breaking things down. So if we focus on this center part of the diagram, okay, this part over here is showing the breakdown of ATP, and that would be catabolism. Okay, and in contrast, this part over here is showing the synthesis of ATP. So a synthesis reaction is to build something. That's anabolism. Pretty much all reactions in the cell can be categorized as either catabolic or anabolic. And they're really all about energy processing. And processing energy is important because we need energy in order to do work. So we've got some different kinds of work listed over here. Cells need to do chemical work, transport work, mechanical work, and I'm sure you can think of other categories of work that cells need to do. They have to get the energy to do that from something, and the immediate source of that something is ATP. Okay, the energy required to make ATP is provided through energy yielding processes, or energy conserving processes more accurately. So we're conserving energy from other chemicals and funneling it into ATP, or we're conserving energy that was found in light and we're funneling it into ATP synthesis. The different ways that microbes go about this are listed over here on the left. So microbes can do aerobic respiration, which is what you and I do. They can also do anaerobic respiration. They can do fermentation, and they can do photosynthesis. Those are the major categories whereby energy can be conserved from the environment somehow and funneled into the synthesis of ATP, and then that ATP can then be harnessed by the cell to do cellular work. Right, now think about what you know about chemical reactions. So here's a simple chemical theoretical reaction. A plus B react to form C and D. The reactants are over here on the left, okay, and the products are over here on the right. Each of the reactants and each of the products has an associated chemical energy, which we refer to as the free energy, or G, and it's G because it's actually Gibbs free energy. Now, we know that every particular chemical has a set or theoretical G, or Gibbs free energy, and by theoretical here this should be like a superscript prime, so it should be G like this, not prime, and that's referring to under standard conditions. Like it's expressed in kilojoules per mole. By standard conditions we mean neutral pH and certain concentrations. Okay, so every chemical has a particular free energy associated with it. If you consider the free energy change inherent in a reaction over the course of a reaction, like as A and B react to form C and D, then the free energy will change over the course of a reaction, and we can calculate that change, and in doing so we come up with a value known as delta G. Okay, and delta G is going to equal the free energy of the products minus the free energy of the reactants. In this case, the free energy of C plus D minus the free energy of A plus B. That's what we mean by that. We can calculate the free energy change inherent in the reaction over time. And that's inherently essential in understanding cellular metabolism, these ideas of free energy. The free energy that we get, the delta G, okay, and here's the equation, here that I just showed you, all right? So the free energy associated with the overall reaction is really important for a lot of reasons. And before I go on, you'll note that there's a little F that's appeared here, and that's the free energy of formation. for each chemical, there is a tabulated free energy called the free energy of formation. It's the energy to basically put the atoms together to make that particular chemical. And because it's tabulated, we can look those things up very conveniently in handbooks and tables, and they're called the energies of formation. And they're pretty much synonymous with just the free energy of the particular chemicals that you're considering. Okay, so with that information, you can take any chemical reaction and you can determine what the delta G is for that chemical reaction. And here we have two different free energy profiles. That's what we're seeing here in these graphs. So we have a free energy profile on the left where the delta G, and it's shown here, okay, and you would calculate that by having the delta G, the free energy of formation of the products, that's what the P is for, minus the free energy of the reactants. So over here on the left, you're going to end up with a delta G value that is positive, right? That is greater than 0. Whereas over here on the right, here are the products and here are the reactants. The products clearly have a lower value than the reactants do. So here you're going to end up with a delta G value that is negative, that is less than 0. Okay? It's negative. So what does that mean, right? We use these terms, and you should be familiar with these terms. By knowing what the delta G value is, we can know whether a reaction is exergonic or endergonic. Exergonic reactions release energy. So this reaction profile shown over on the right is showing us, oops, my pen doesn't want to write here, exergonic. Okay, it's an exergonic reaction. And over here on the left, it's an endergonic reaction. Okay, on the left, in the endergonic reaction, you would have to actually put energy into that reaction in order to make it happen. Okay, this is a reaction profile that's very typical for cellular reactions that are anabolic. Over on the right, if that reaction will happen, it will release energy. That's very typical for reactions associated with catabolism, where we're breaking molecules down. Okay, so catabolic reactions are typically exergonic or energy releasing. Anabolic reactions are typically endergonic or energy consuming. So it's relatively easy to imagine how catabolic reactions could proceed, and in fact they do proceed spontaneously, which doesn't mean quickly, but it means that it's thermodynamically possible. Okay, but it might be harder to imagine how the cell manages to conduct endergonic reactions. How does it make that happen? And the link, of course, is ATP, and that's what we're going to talk about next. All right, let's say, before we start thinking about ATP, let's keep thinking about delta Gs. And let's just say that you did not know whether aerobic respiration was an exergonic or an endergonic reaction. And of course, you should know that aerobic respiration is exergonic, but let's just pretend that you didn't. How could you figure this out? You could figure it out by calculating the delta G values. So here's aerobic respiration. Here's the summary equation. Okay? C6H12O6 plus oxygen. Okay? These are the reactants. They react to form carbon dioxide and water. That's what goes in, that's what comes out. These are the products. Okay? The free energies of formation for each of those chemicals is tabulated. You can look it up in the appendix of your textbook or online or numerous physical chemical handbooks. And they are, I'm talking about the energies formation, standard conditions, which will work for our theoretical purposes. They are 917.3, okay, and that's a negative value, very important to remember. Oxygen is 0, making it really easy to work with. Carbon dioxide is negative 394.4. Water is negative 237.2. I'm not writing the units in just to keep the screen a little simpler to look at, but if I was doing it by paper, I would include the units, and the units here are kilojoules per mole. To account for balancing the chemical reaction, which you have to do in order to do these calculations, you have to balance the reaction and then you have to apply that balancing to the math. Okay? So in a balanced aerobic respiration reaction, there's 1 glucose molecule, 6 oxygens, 6 carbon dioxides, and 6 waters. Okay, at its most simple. So if we factor that in and we multiply all of those by the number of moles that would be found in a balanced reaction, if you multiply 917.3 times 1, you're still going to get 917.3. If you multiply 0 by 6, you're still going to have 0. But if you multiply negative 394.4 by 6, then you are going to end up with negative 2,366.4. And if you multiply the water value by 6, you are going to get negative 1,423.2. Okay, so we'll put these in just for the sake of being thorough. This is a 1. Okay, we still have negative 917.3. Okay, now let's organize that a little bit differently. Here's our reaction. Delta G, working with these theoretical formation values, is going to be the free energies of formation of the products minus the free energy of formation of the reactants. Okay, and the products, remember, are over here on the right, and the reactants are over here on the left. If I sum these together, I'm going to get negative 30,789.6, and I'm going to subtract this value over here, okay, negative 917.3, because the 0 contributes nothing, and I'm going to end up with negative 2,872.3, and the units are kilojoules per mole. Okay, that is the delta G associated with aerobic respiration. The fact that this is negative tells me that this is an exergonic reaction. And the fact that this is actually a pretty large value tells me it's indeed a very large amount of energy that is released. It takes about negative 31 kilojoules per mole to make a mole of ATP, and so we can make a heck of a lot of ATP using this particular reaction. This is why aerobic respiration just really rules. You get a very large, very negative delta G value. All right, let's move on to the next part of the lecture.